sorry, I was sick in the winter school. So this is definitely a lecture intended for the winter school. It's intended for postgrads. It isn't really on philosophy. If I won't be at all offended if you walk out because there's no philosophy. Well, there's some philosophy in here, but there's not a lot of philosophy in here. I think what happened is Melissa looked at the program. There were a whole lot of people speaking on model evaluation, and that sounded like things were being duplicated. And I've been accused of erring towards the philosophy side before, so I think that was an easy discretization to make. Okay, so but it's philosophy in the sense that the sort of the aim of the exercise here is to really make you think a little bit harder about the models you use, and I think most of you do use models in your work, because inference with models is a tough game, I think. Right, so what am I going to say? I'm going to try and talk a little bit to each of those points, really basic things. It really is kind of a lesson-y type thing. And it's not necessarily that what I'm going to be saying is true, but it's what I'm going to be saying should help to make you think about what you're doing a bit. That's the aim. So what is a model? Why are models hard to use? Why are models hard to use is just anecdotes really for you. What makes a good model, I think, is a tough question. Some interesting things to think about with measuring model performance, and then sort of where climate modeling is at the moment, where we're using ensembles to try and understand everything, and some of the difficulties we might have with that. Okay, so what is a model? It's anything that fits that definition, right? It's a simplified representation. A painting is a model because it represents some bits of the system that you think are important. Okay, that is a model. All it has is it has some stores of carbon and some indications of where the fluxes go. It's a model. This is a model. If you had some things constant, it could be the ideal gas law. It could be anything you wanted it to be. That's more like the models you know and love, right? But it could be lots of different things, right? So one way to think about when you are dealing with models is the bits you have to go through when you're building a model. So I like to think of sort of the stages you go through where you identify the features of the system you're interested in. You then try to say, okay, what are the relationships between those particular features of the system? Then you say, well, how do I codify that into some kind of mathematical relationship? And then I have to make a whole lot of assumptions to actually solve that on a computer system, where I have to have some kind of way of solving the equations. I have to make some choices about spatial and temporal discretizations. And there are lots of assumptions you make in each stage, obviously, and we'll get back to that. So as far as I'm concerned, this is the toughest one for a postgrad to work with. Okay, a model's definitely not reality, and it's your job to understand how a model differs from reality. And it's never reality, right? Never make the mistake of thinking that. And they're never 100% correct. So why aren't they correct? If you haven't read this paper, it's fun. I really recommend it. A modeling system is a closed system. At the outset, you know everything that can affect that system, right? And the real world is totally different to that. You have no idea what might affect the real world. There might be a whole lot of things that aren't in your model. There might be things that are in your model at the wrong resolution. Lots of things that you don't really understand can affect the real system. Further to that, there are lots of relationships in a model that are either empirical approximations and not physical laws, or I'll get to a minute, and discretization is also another reason. So when we don't really have a good understanding of how something works, we tend to take observations and fit curves to it and then predict it using those curves. Yep, that's what I mean by an empirical approximation. And the land surface, which is my background, is rife with that sort of stuff. Photosynthesis, lots of processes where we've got lab results and we try to fit curves to them and use those for prediction. Critically, even if you could have physical relationships, because of computing power, we have to use time and space scales that don't really allow us to represent all of the scales. Like convection is a classic example. We can't really resolve convection at the global scale yet because of computing power. So we end up parameterizing things for net effect. Okay, and obviously there's some approximation that goes on there. And obviously we're going to be missing some bits in the real world that are not in the model. But models can obviously be very useful. So the question is, how do you know when they're useful? So we'll try to cover that. So just a bit on particular processes within models. Obviously, if we have physical laws that we think cover systems, we'll use them in a model. This is what I was saying before. Otherwise, we'll use empirical approximations. Obviously, any particular process in a model could be at the level of first principles. We think we understand it really well. We've got the equations that actually describe the physical process. Through to heavily parameterized, we might understand it, but we can't represent it at the right scale, or we fitted it to lab results. Through to we assume it's constant. Through to we just don't include it. Okay, so any process you care to think about will be one of those four. And if you're a little bit uncomfortable with this distinction between what's physical and what's empirical, have a think about whether the particular process has free or at least unmeasurable parameters. Right? So an empirical model doesn't do anything until you calibrate it. If you had a purely physically based model that described a physical system perfectly, it doesn't need any calibration. All you need to do is take the measurements that describe the system, it gives you the answer. Okay? So you can take the physically based, nominally physically based approach at a very coarse resolution, and you're going to have to parameterize it, the net effect. Okay? And as soon as you do that, you take what's nominally physically based and move it up towards it being empirically based. Okay? So you then make it have particular assumptions about functional dependence, spatial scale, temporal scale. As soon as it's empirical, it has some of this. And that's, I assume you have heard about coupled models working at particular resolutions. You try to switch a coupled model to a different resolution, it doesn't work. That's part of the reason why. Okay, this is a little more woolly. Why are models so hard to use and understand? This is partly because of the funding situation and the fact that there aren't many people working on the same bit of science. People write models for themselves. They're commonly developed for a particular hypothesis and then applied more broadly. I think climate model components are very much in that category. I think you know that's true. Similar to the second point, coupled model components are written by different groups and they get brought together and tied together with variables that are nominally the same, but often the feedback processes that actually go across the borders of these models. And if you were constructing an ideal group to work on it, you might want, for example, somebody who did fluxes from the land and lower boundary of the atmosphere people to work together, but that often doesn't happen that way. So different people work on different bits, and a lot of people are involved, so that's part of the problem. This is also a big part of the problem. Funding agencies don't really give you money to go and work on, hey, I'd like to improve this particular bit of the model. I think I know how to do it. They give you money to go and do new things. They're exciting. So it's something you've got to kind of pick up along the way. The environment is not perfect. And of course, our community, like lots of other places, love annoying references or names that yield meaninglessness. Acronyms. Okay. So this I put in a paper, I think it was about 10 years ago, and it was really relevant then, and I don't think it's that relevant anymore, which is a really good thing. Okay. So there are two columns. This is the bad column, this is the good column. You can read through them. But certainly when I did my PhD, which wasn't that long ago, all the models I came across looked like that column and not like this column. But I think now there are more models that I come across that look like this and look like that, which is kind of down to the people my age and younger who have implemented some standards, which is great. But don't be surprised if you find that kind of stuff. Okay, so that was the anecdotes from why a model is hard to use. What makes a good model? Most people, when you ask them, will give that answer, that a good model is the best performing model, which I think is a terrible answer to the question. That's a slightly better answer, but I don't know. There are lots of versions of that. You can come up with your own version of that. Because what the system is, you've got to define, and what the particular variability you're looking at, you've got to define. But there are lots of ways you can look at what makes a good model in terms of how much information it's been given and whether it utilizes that information well. Okay, so critically, you can have a good fit to observations and not have the mechanisms right. So looking for a good fit to observations as a good model can be problematic. Okay, I don't know if you know this paper. It just gives this example that a lot of people know outside of this paper, which is predicting the motion of the planets through the night sky. Who knows this example? Ptolemaic model? Epicycle model? No? Okay. So this guy Ptolemy had this great idea that came up with a really good model that fitted your ability to predict the motion of the planets in the night sky. And of course, because everyone knows it's true, the Earth is at the center of the solar system, right? And orbiting around the Earth is an imaginary object, okay? It's not real. I can't remember whether it wasn't real or it was just something you couldn't see. Then orbiting that, there was another imaginary object at different radii and orbital speeds. And you kept going until you got to the planet that you wanted to predict the motion of. And if you calibrated those parameters very carefully, you can get a fit that's better than Newtonian mechanics, right? So how do you know that the Newtonian Copernican model is better than this one, if this one fits the data better? So these guys go through trying to quantify unsupported parameters. Can I go and measure these parameters? No, because they don't really exist. They're imaginary things. It's just an empirical model, right? It's like a multi-stage regression or something like that. So to fit to the data, empirical models work incredibly well, but in the case of the Newtonian model, each one of those things you could go out and measure. So that gives you some indication. So this is the degree of overfitting. Shouldn't be worried about this one, really should be worried about this one. So this is just a list of things that, if you're trying to think about a good model, I think are important, or rather, if you're trying to think about whether a model's performance is good or not good, you might want to think about. So if you had a model that, two models, one is more complex than the other, you would expect the more complex model to give you a better simulation than a simple model. Yep. And in this case, I'm talking about complexity in terms of its functional representation or how many internal parameters it has. Then you might think about how much information it's given in inputs. Yep. How much, so this is partly my land surface background, right? Where the land surface, rather than artificially, is viewed as being forced by meteorology and produces fluxes into the atmosphere, right? The amount of information you can get from shortwave radiation is a lot, and you can actually predict fluxes pretty well just from that. But once you give it temperature as well and humidity and more, you get closer and closer to the real answer. So the more variables you give a model that are pertinent to the thing it's trying to predict, the better your answer should get. Okay, so these should go some way to telling you whether your model is good, to say, okay, is it giving the right level of fidelity for the amount of information I'm giving it? Obviously, this is a question of empirical versus physical, which we were talking about before. And critically, if you're trying to evaluate it, you have to test things out of sample. This is where the difference between an empirical model and a physically based model really gets picked out. If you don't test out of sample, you don't find anything. Of course, you can come up with a set of weight and climate models that does a brilliant job if you test it on the data that you derive the weights on, okay, or something like that. It doesn't really tell you whether it's working. You need some way of testing out of sample. And out of sample can work in lots of different ways. You can go out of sample temporally, you can go out of sample in space, you can go out of sample in lots of different ways with different metrics, lots of different stuff. Okay, measuring model performance. How quickly am I going? Very quickly. Oh boy. Okay. So the first four of these should be really obvious to everyone, I hope. And it's just saying that when you make a choice about your cost function, your temporal representation, your spatial representation, and which variables or observational data sets you do to assess performance, you're going to get very different answers. Those choices matter a lot. That shouldn't be a surprise, but it can give you totally categorically different answers. This last one I'll spend a bit more time on because it's one of the bits of philosophy in the course, in the lecture. And it's an interesting one, and I think it's one that doesn't get talked about enough. Okay, but the first things should be really obvious. Okay, this is a really well-known paper, you probably know, Peter Gleckler, that's just pointing out that if you look at all these different models and a whole lot of different metrics, there is no one model that performs best in everything. Okay, so you choose a particular variable, you can be sure that people who were talking about this particular climate model would go and give talks about this metric when they went and talked about their climate model overseas because it looks pretty good in those metrics. Okay, and you can pick out how it's going to work. And that's not always conscious, right? But you tend to, confirmation bias is pretty real and everyone has it. So when you look at your model, you look at the results across all the different things and you tend to focus on the things that were really good and you go, hey, it was really good model. I just forgot about the bits where it was really bad. People do that, okay? You will do that, I do that, but you have to be aware of it to really have a ledger. That's why people have standardized tests and stuff like that. Okay, so this is just about different variables making a difference. Similarly, if you choose particular gridded masks spatially across the globe, look regionally, look zonally, or look global averages, you could get a totally different indication about which model is best in each one of these. Likewise, for your model, you'll get different indications of how well it's performing depending on which particular spatial representation you choose. Okay, no surprise. Same thing for temporal representation. Obviously, if you go from fine timescales down to longer timescales, you're losing more and more information about the prediction, but you could also get very different answers. So you could get a perfect annual average year to year and have the seasonal cycle entirely out of phase. Totally possible. So if you looked at monthly correlation, you'd be the worst. If you look at annual averages, you could be the best. I mean, it's a constructed example, but that's okay. Then there are obviously things like frequency domain measures, like a Fourier transform that looks at variability across the whole time series, a wavelet transform that looks at variability across a moving window of the time series, that gives you, instead of indication about what happens in time, what happens in frequency space, right? And obviously you can look at things like PDFs that are independent of time. You aggregate everything together in a distribution. This tends to be what you look at with actual climate models, because often the internal variability is out of sync, right? But just pointing out that, again, your choices of the temporal metric will make a big difference to what kind of answer you get in terms of evaluation. Same with cost functions. There are lots. And this is a really awkward graph from a very old paper, which is just pointing out that whatever this horizontal axis is, RMSE gets better as you go through time, and actually the scatter in a particular regression plot gets worse. It's entirely feasible that one metric will get worse along a particular axis, and a different metric will get better along a particular axis with the same data. So again, choice of cost functions matter. There's independent information in different cost functions. Okay, this is the fun one. Confirmation holism, or epistemological holism, and underdetermination. So this is one of the early quotes about it. So this guy was a physicist. Yeah. If the thing you're expecting to happen doesn't happen, not only does it put into question what you're trying to find, like, is the thing I was testing for not true, but it should also make you question all of the apparatus that you've used to put together the experiment. Does that make sense? I'll get to how this fits into climate modeling in a second. So another way to put that is no hypothesis can be tested in isolation, only under the assumption that the theories on which it relies are correct. So if you think about that in terms of climate modeling, you can think of, this is not quite right, but you can think of a climate model as a chain of particular hypotheses or parameterizations strung together, right? So if you can only evaluate whether it's right at the end of that chain of processes, you could get the right answer because this one chooses it too high and this one chooses it too low, and the output after you've gone through both puts it in the middle and gets you the right answer. So you've got no way to tell if you get the right answer, whether it's for the right reasons, or if you get the wrong answer, you don't know why, you don't know which part of the chain is to blame, because you're under constraint. So the point of this is that the meaning or the confirmation is the end result of the process. It's holistic. So confirmation holism. The confirmation is holistic of the whole system. You've got a climate model. You don't really get to say, is this bit right? Is this bit right? Is this bit right? Is this bit right? Yes, all the bits are right. Let me put them together. You get to string some things together and then test it at the end. Okay, and that's problematic. Okay, or it's difficult at least. So let me just see if I can skip forward. Yeah, okay. Okay, so I mean, a simple way to think of that is if I take a climate model and I want to change in a different convection scheme, okay? I swap in a new convection scheme and it gives me a better global precip field or a better global temperature field. Is that because the convection scheme is better, or is that because that new convection scheme has better compensated for the existing biases in the modeling system? How do I tell? You can't, right? So this is all about the fact that we're engaging in something where we're fundamentally under-constrained by the data we have. We can't tell whether every step along the process is right, I think fundamentally. Okay. So there's a really cool paper, if you want to read it, by Leonard and Winsberg, where they talk about how did climate modeling end up in this situation. And they talk about fuzzy modularity. Okay, this is exactly what I was just saying. That's what I was looking for and I didn't see it. So they talk about a perfect representation then being the one that compensates for the existing biases within a model. Yep. Parameterizations become dependent upon each other. Anybody who's worked in a coupled modeling system for a long time knows about this. Yeah, this is true in the access model. This is true that the joules has too much evapotranspiration. The atmospheric model compensates for that. You can't put in a land surface model that has about the right amount of evapotranspiration without mucking up the global climate. And because they're different process teams working on it, it's very hard to get them to make the change at the same time. Right? So parameterizations become dependent upon each other. And model values become effective values rather than actual values because there's this compensating process. And they talk about kludging or kludging if you're from the States, which is, you can ignore, this is straight out of a dictionary, but you can ignore that one. I don't think that's what it means. It's more like this, right? You've got a whole lot of people who have worked on different things. People build atmospheric models to understand what happens on continental boundaries. Okay, initially, that's kind of what Manabe and all these guys were interested in early on. Then you've got people who are really interested in ecosystems and they built land surface stuff. And you've got people interested in, you know, all sorts of different things. They said, hey, these variables can be plugged together. Let's make a big model out of this all. But that means that it's not a holistic view that put it together. It's a whole lot of different interests that came together. So they talk about fuzzy modularity and they talk about this kludging. So that modifications to improve. So you end up with this collection of things that come together. It behaves chaotically. So your only levers to pull to make it behave are sort of this mix of principled and unprincipled steps. So I don't know if you know that in lots of climate models, they actually have to pull the solar constant up or down, or there are different things that get done to get the model to roughly behave. The climate that they come to an equilibrium is very rarely, for example, annual average temperature in line with observed annual average temperature. You look at the change in the model to look at the change, okay? Because it's very hard to pull levers to get everything to behave itself. It's a very complicated beast. So what are the rules governing model tuning? There aren't really that many. I think in CMEP 6, they're going to try for the first time to document model tuning stages that go through to produce CMEP 6 simulations. It's really hard. And this is not meant to sound super critical of what's going on. It's meant to give you an indication how hard it is to get these things to behave. Okay, so all of this stuff boils down to the fact that we don't have enough observations. We're massively under constrained. This is also not quite right. So it goes away when you have observational completeness. And I've written here when we have observations for every variable and parameter in the model, for every location, at the resolution of the model for the entire evaluation period. That's maybe not quite true because neighboring grid cells are not independent of each other. And if you want to say it's lower dimensional than that, it's true, but it's essentially that, right? And even once we have that, it doesn't mean we're going to have a good model, but it means we can actually start to evaluate what's going wrong a bit better. Okay. Obviously, if you take models to higher resolution, that doesn't help it. We know there are lots of benefits of going to high resolution. We resolve convection and a whole lot of emergent phenomena start to come out in these models, but that doesn't make this problem better. And adding more processes doesn't make this problem better. Yeah? So a lot of the calls, this is kind of where you get funding. But both of these things will introduce more degrees of freedom into the modeling system, effectively. So more things to go wrong in some ways. Okay, which leads to this flowchart, which I love dearly, which I think exemplifies some of the things that I've just been talking about in a different way. So just keep in mind that some people who've engaged with models for a while enjoy this, that in developing a model, you start with sparse and infrequent observations. You've seen this, Melissa? Maybe not. You make some incorrect interpretation of those observations. You have preconceived ideas that you bring to the table. You arrive at a theoretical misunderstanding of how the system works. you make some unrealistic assumptions about the measured processes, some coding errors, and you get an extraneous and unwieldy model, right? Extraneous means it's unrelated to the system that you're interested in, and it's hard to use, okay? So then you notice that it doesn't agree with observations very well, and so you add more parameters to make it more flexible and more like an empirical model. So then the model's under constrained by available data. You can calibrate it beyond physically reasonable ranges, yeah? Then you can find some metrics where it looks pretty good. Then you have some coincidental agreement between observations and the model, and you can publish. Right? So why is that funny? Probably because it's a little bit true sometimes, right? But some of that other stuff about empirical models being an issue, that's this bit, right? And the lack of constraint with data, how do you make all these mistakes? Because we don't have enough data, basically. And it's funny because sometimes in retrospect you realize that's what you're doing, but you didn't think you were doing it when you did it. Okay. Last bit. Uncertainty in ensembles. So this is how I think about any model, a climate model or a different kind of a model. And I separate inputs to a model, time varying and time independent, only because the definition of what the model actually is really critically dependent on those things. So these are things you put in there that just don't change. Like if you were doing a weather forecast, the vegetation would not change, for example. If you're doing a climate projection, probably the distribution of rocks of the land shape would not change. If you're doing it over millions of years, everything would change. I don't know. Okay, but for the particular simulation. So for a climate model, that looks like the time varying inputs are things like carbon emission scenarios and solar radiation changes and maybe human land use changes. Parameters might be surface properties, physical constants, parameters for empirically approximated processes. And the state of the system in the past, this is obviously a tough one. This is what means that climate models are out of sync with observations, and where weather forecasts and climate models are very different is basically just in this bit, how you initialize them. I've got a separate box over here for output, but typically the output is the same as this bit, but it might not be, depending on what kind of diagnostics you're interested in. And the way we try to think about uncertainty or deal with uncertainty is put some kind of imaginary PDF on our uncertainty in each one of these things. I'm not pretending those distributions have any shape like that, and propagate that through the model to the output by essentially sampling, doing something like taking model parameter set 1, model input 1, model state 1, making prediction 1, and doing it over and over again. You could estimate equally plausible different variants of that, and you propagate it through. Okay, and then you get your ensemble. And you get a histogram, or you can use a density function to make it look like a PDF if you like. So this was, many years ago, a classic example of this, had CM3 with perturbed parameters and initial conditions in climateprediction.net, where they estimated a particular temperature change in the future. And that was obviously called the probability of a particular temperature rise, but I want to make the point, it's not quite the probability of a particular temperature rise, because it's conditional upon a whole lot of different things. Yeah, I'm sure you can imagine some of the things. So the first one that I want to point out is this cascading uncertainty problem. So you might think, well, how is that related to this? Well, how you choose those particular parameter values and initial conditions is really important. How you choose the emission scenario is really important. And at the moment, all we can do is start with particular emission scenarios, run Earth system models to get a spread of results for each one of them, choose a subset of those only to do regional downscaling, choose a subset of those only to run an impacts model, and then get a spread of impacts, because we just don't have the resources to do all the possibilities, right? So the way it typically works is there's a ballooning of uncertainty, you make some aggregation or simplifying assumption, there's a ballooning of uncertainty, you go on and on and on until you get to whatever it is you're interested in. But that's what you really want, is what that looks like. What does this energy distribution look like? Yep. Okay. So it's a tough thing to do. We don't have the resources to do it very well. And we're not very good at working out how to sample that well yet. Just because we can't make very many choices. We can't really afford to make mistakes. We decide on how to do it and we just have to do it. And the result is what it is. We're still at that sort of stage. So that is the first problem there in terms of what is wrong with an experiment like that. the choices are the choices made, and are very hard to say that that is actually, how do you defend the choices made of parameter values and initial conditions and emission scenarios so that that is actually the probability of a particular temperature rise? It's very hard to do. Okay.
What's the black one again?
They were two different ensembles, short-term and long-term ensembles. Yeah, it's just a picture to indicate. It was actually a picture from clientprediction.net, but the principle that I'm kind of getting at. Okay. So the second problem with this is that you can sample uncertainty here and here and here, but we haven't really got in an experiment like that one sampling the uncertainty in the model space, and that's a much harder thing to do, right? Because okay, there's just interchangeable terms here. My point here is that those things are real number spaces. We know how to get PDFs in there. We know how to sample values from there. We know how to do ensemble runs from there. We don't really know how to sample this. This is kind of like a functional space with an attractor that looks like some of our observational data sets that are just not very well defined. So if you think about what sits in this model space, okay, so we know how to do uncertainty here, here, and here, but not here. So if I want to go back to this slide, okay, these are the steps in building the model. This top step defines the variables, the input space, the parameter space, and the state space. That's identifying the features of the system you want in the model. All the decisions you make about how they're related, how that gets codified into equations, how that gets put into a numerical model, how you actually implement that, how you do the aggregations, that stuff all fits into the model space. It's arguable that most of the assumptions, once you've decided on your variables, fit into this model space bit. There's a lot wrapped up in that. Okay, so a better answer here is that might be, assuming the sampling were done well, that's actually the probability that at CM3 will simulate a particular temperature rise, which is a very different thing. Okay. So if we really wanted to get towards a probability of a prediction, we would need something a little more like this. Yes, independent estimates of parameter values, independent estimates of initial conditions, but also independent estimates of the model itself. And of course, that's where things like CMIP come in, right? So that's how we get to CMIP. We want lots of different model structures. So you've probably seen figures like this. This is already pretty old. I think this is, yeah, that's very old. Okay, but there are versions of this figure in the newer IPCC reports. The idea here is the color you can see is the multi-model mean. This is now temperature difference, December, January, February, June, July, August, between 1980 and 1999 to 2080 and 2099, average of those two periods. What's the difference? That's the multi-model mean difference. This is the same thing for precipitation and pressure. But in this case, what they've got is stippling these dots over the plots. There are lots of dots here, but not many there. The dots are about where 85, 90% of the models agree on the sign of the change, okay? So the conception of producing a plot like this is to say, where we have model agreement, we're more confident. Okay, so that is the idea here. Where we've got many independent estimates of the model itself, we're more confident. But it's a key question then, is agreement actually a sign of robustness? So for example, if 90% of the models in CMIP were in some way effectively identical, then having 90% of the models agree wouldn't tell you anything. Okay, I'm not saying they are. I'm just saying if that were the case, it wouldn't tell you anything. So how do you tell how different the models are? How do you quantify the degree to which they give you independent estimates of that model space effectively, right? Right. So the story goes something like this. Modeling groups share literature and data sets and parameterizations and even model code. So then how independent are the models actually? Yeah, and how should we go about defining that? And there are at least two ways to think about that. One is you could say, I'm going to do it based on the simulation values. I'm going to look at their outputs and see how similar they are. The other way to do it would be something like saying, I'm going to look at the genetic evolution of the models. Those that have similar treatment of structure, treatment of process, I'm going to treat as dependent. Those that have diversity in treatment of process, I'm going to treat as independent. But it's trickier than that, because you can imagine that where you have tight observational constraint and you know what the observations say the system should look like, you want all the models to agree close be similar to that. And where you have no observations, you want the models to have a diversity of opinions, right? So that's saying you can have a model that is independent in some respects and not in others. So it could be quite a cloudy picture, is my point. But just to try and give you a very hand-waving indication of how to think about independence. Okay, suppose I were trying to estimate that this is a hill, okay? You can tell it's a hill, right? And that's the top of the hill across. And I was trying to estimate where the top of that hill is. And the way I'm going to estimate the top of the hill is I'm going to send you all up with your mobile phones to climb that hill, and you're going to text me your GPS coordinates every 2 minutes, okay? There you are, 4 of you climbing the hill, texting in your coordinates, and I estimate the top of the hill by averaging your coordinates while you're climbing the top of the hill. So there's my estimate, pretty good estimate of the top of the hill, even though you're nowhere near the top of the hill, right? So this is like your ensemble, yeah? You're on particular models in your ensemble, there's my observational target in the center. There are reasons why this model's flawed, by the way, but it's a good indication to get your head around the problem. Except, of course, if you all start climbing the hill from the same side, then I can average your coordinates, and I don't get an estimate that's much better than any individual model. Does that make sense? So this is something like a model space, and spread around there is something like model independence, but it's only a hand-waving indication, and I actually don't think the observations are in the middle, but we can talk about that later. So spread is something like an indication of dependence. So keep in mind, in this case, all of the models are further from the target than here. These are all closer than those ones, but the ensemble mean in that case is a much better estimate because they're more independent. And I'll give you a concrete example of that in a second. So a good way to think of this that I think is quite useful is to think in terms of error correlation. If this is a model minus OBS time series for 2 different models, you can see those are relatively uncorrelated. Those 2 are much more highly correlated, so there's more dependence in the bottom one. And you've probably seen a plot like this, although this is actually just noise. This is just a plot of noise that's scaled in the right way, where OBS might be that black line, the yellow lines are different models. And if I take the multi-model mean, what it ends up doing is giving me the best estimate of the forced climate signal or something like that, okay? So this might be the warming trend and plus the internal variability of the OBS. The models should have internal variability that looks something like the OBS, and the multi-model mean ideally would give me something like an indication of the warming trend. So in this case, you would want the models to be as anti-correlated as possible so that the internal variability doesn't end up in the multi-model mean. Okay. How many of you seen these slides before? Some of you. Okay. So these are Naja's slides from a 2018 paper, which I think give a really simple indication of this problem. What we're going to do is we're going to take CMIP5 simulations, about 80 of them, and we're going to take a subset of those. Yep, of size k. So we've got n, and we're choosing k less than n. And we're going to do that in 3 different ways. We're going to randomly choose k. Yep. We're going to choose the best performing k simulations against a particular target. And in this case, what we're looking at is what I'm going to evaluate here. So this is the mean of the entire CMIP5 ensemble here against an observational product. And this is going to be the mean of the subset against the same observational product. Okay. How can I subselect this so I get a better effective sort of regional climatology is what I'm looking at. So I'm going to choose the best K performing against that observational product. And then I'm going to choose the best K simulations whose mean has a minimum RMSE against that. Okay, so that's like an optimal choice, right, for this metric. So just to make that clear that that's not necessarily an easy thing to do, no, you did a good job of finding a solver to do this. For example, if I choose a subset out of 81, I want 40 ensemble members whose mean is best against observations. There are that many possible ensembles to test, right? So you can't just try it with brute force. You've actually got to find a way to do it cleverly, which was thankfully we did. But the results are kind of interesting. Okay, so what we have here is root mean square error. In this case, it's against surface temperature, had crew T4. This is the K, which is a subset of the N. N is 81, so once I choose 81 from 81, the RMSE is the same, no matter how I choose them. what you can see is that the lowest RMSE, of course, is if you choose the subset so that the mean of that subset, it minimizes RMSE against observations. Of course, that's the best answer. That's the black one. But the point that I'm choosing this to illustrate is if I choose the best performing K ensemble members and I take the mean of those, I will very often do worse than if I randomly choose. Yeah? So if you want to take a subset and you're interested in the ensemble mean, do not choose a subset based on performance unless you know there is independence amongst that subset. So what tends to happen is I start choosing ensemble members from the same model. So I get, they're good performing ensemble members, but what happens is that they don't provide any new information. And actually my multi-model mean doesn't get any better. Whereas if I'm randomly choosing, I'm introducing more information to the ensemble so that the mean gets better and better performing. So there are quite a few circumstances that if you choose an ensemble by best performing individuals, your multi-model mean will be significantly worse than if you'd randomly chosen them. That usually happens to some degree. Okay, these are different variables and different data sets. It's not always such a clear picture. Sometimes the green line only goes above the blue line at high ensemble, and sometimes not at all. But often it does. Okay, there are lots of different versions of that. But just to warn you that when there is a high level of dependence to the ensemble, which will be even more the case in CMIP 6 than it was in CMIP 5, you need to be really careful about how you choose an ensemble subset or how you weight your ensemble, because choosing by performance alone can be seriously counterproductive. Okay. So you could kind of see that this was going to happen. So this is a plot of all of those 81 versus all of those 81, and this is error correlation when I talk about error against our crew T4, the same data set, okay? So high error correlation above 0.9 is this black color. And what you can see is that, for example, Mark 3.6, CCSM, all the models, you can see they're blocks. So all the runs from the same model have highly correlated errors with each other. And even more than that, you can see particular groups where there is dependence. So here is access and HadGem, highly correlated errors. Not surprising, right? They have the same. So when there was this, you guys are probably a bit young for this, there was a debate, should we get access in or should we further develop Australia's climate model? I remember standing up and saying, if the purpose of developing a climate model is to contribute to CMIP, even if we make a worse climate model with uncorrelated errors, that will help the ensemble. It didn't go down very well, right? But you can see that models that share structure have highly correlated errors. So that means if somebody takes CCSM, which is a great model, and imports it to be their national model, it's not really helping CMIP at all. In fact, that means you have to disentangle, do more work to disentangle CMIP to make it useful to you, whatever you're going to do, the more redundancy there is. Because it's going to be a larger collection of good performing models, the more risk that people think, okay, these different models are from different institutes, I'll choose them as independent estimates, and actually ensemble mean will look very much like any individual one of those models. I think this is the last thing I want to say. So this is an interesting piece of work that Ned did, which is related to this. We took a predecessor of that Mark 3.6 model and generated ensemble that was entirely from structural perturbations to the model, parameter perturbations to the model, and initial conditions perturbations to the model, and then looked at the pairwise error correlations between all those simulations. So when you perturb structure, you get massive, so this is from 1 to, well, minus a half, I guess it's about here. You get huge differences, highly correlated versus anti-correlated in the structural ensemble, parameters less so, and initial conditions were all up at around 0.7. And when you compare that to CMIP, you can start to see what's going on. So this is all the pairwise error correlations in the CMIP ensemble. So you can see the structural diversity here and the within ensemble diversity there. There's two separate bits of the distribution. It's a bimodal distribution.